Welcome to the Problemas channel season 2 episode 19, the episode which I have titled Effectiveness of Advertisement. That title is admittedly a little bit awkward and a little bit clumsy, but at the minimum that title is honest because in this episode we will discuss precisely the effectiveness of advertisement from the standpoint of mathematics. Before we do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section find the episode titled The Problemas Channel How To. Watch that episode in its entirety and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2M21, we're given a company, C, that carries out an advertisement campaign about a product, P, and the company carries out that advertisement campaign only once. For demonstration purposes, let us assume that the company advertises the product P over television, in newspapers, in the means of transportations, trains, subways, airplanes, on the posters and billboards, or over the internet, and so on. And we're also told that NA, or the number of the people who may be interested in that product, or the so-called target audience, where with the subscript A we designate exactly the word audience, target audience. That number is known and given ahead of time. And the challenge in this problem is to construct a single variable real-to-real function, to which we refer as x of t, that captures a number of people among the target audience who are aware and do know about the product P. And it is also should be understood that in this problem, once an advertisement campaign was carried out, the rest of the information about the product P is distributed by the word of mouth. Because we will be doing quite a bit of writing in this problem, it is a good idea for you to put this video on pause, go get a pen, a bunch of paper, roll up your sleeves and go to work. Meanwhile, I will prepare the board by erasing the problem statement, which we all now understand, so that I have enough room, of which I will need plenty. Instead of taking the solution of the given problem head-on, we will execute a maneuver that is quite popular across all hard sciences, mathematics, theoretical physics, and computer science. And instead, we will first work with the material that we think we understand a little bit better, and the material which we feel more comfortable with, in order to develop a better feel and a better understanding for what is going on with these type of problems. Once we develop a better feel for what is going on with these types of problems, we will construct a solution of the given problem, of the original problem, by analogy. And speaking of by analogy, if you're looking for a good read, then I hear that recently one of the bigger projects in mathematics, the project of um, translating and making all the technical work of the Swiss-born mathematician Leonard Euler, has been complete. His works are apparently available to the public, and as such, I highly recommend that you read at least some of the early Euler's works, because Leonard Euler was an absolute master of working by analogy. And famously, Leonard Euler, where other mathematicians have failed, was able to successfully evaluate, for example, the following quite famous in mathematics infinite sum of reciprocal squares of consecutive counting numbers. This sum over here. And the way he did it was precisely by analogy. Later on, maybe in the future episode, I will put together a way to evaluate this particular infinite sum using the machinery of complex numbers, contour integration in the complex plane, and residues of holomorphic functions. But these are different details. For now, instead of studying the propagation of information across people over time, we will begin with material that all the members of our community should be able to understand and associate themselves with. That is, we will first study the time evolution of population of single cell, let's say primitive organisms of a specific chosen or fixed type. And we will frame the relevant problem as follows. Given an initial size of such a colony, we want to know the population of that colony at an arbitrary time t. Because in this episode and the couple next ones, we will be studying the mechanics of the equation problem solving approach. Remember that the first step that the equation problem solving approach prescribes us to carry out is to introduce as many variables as needed. How many variables will we need in this case? Well, the nature of this specific problem pretty much dictates that we deal with two variables. One variable we will call t. This will be time. And the other variable will be the number of single cell organisms at that particular time. We will refer to that number as x, like so. And across these two variables, the variable t will be independent. It will vary pretty much and initially under our control. For example, we can measure that variable in days, for example, but the variable x will be our unknown, and the number of such unknowns directly relates to the words one-dimensional in the title of this segment that you saw a few seconds ago. And in the theory of differential equations, the number of such variables or the number of unknowns that completely describe the behavior of the given system is called the dimensionality of this problem. And to this parameter, let's say, from the theory of differential equations, the dimensionality of the problem, there exists a direct analog in theoretical physics, and that analog is degrees of freedom, or a degree of freedom. As such, in our problem, we think initially that precisely one variable, one unknown, is enough to describe the behavior of the given system completely and fully. Next, we remember that the equation problem solving approach prescribes that once we introduce as many variables as needed, we construct as many equations as possible. And right now, that order is a little bit too tall. Before we get to the construction of an equation, we need to wrap our brain around and see how we can prepare the material, the fodder, for the construction of an interesting equation. Well, also remember that a couple episodes ago, when we explained how the equation problem solving approach works, we, along with Isaac Newton, observed that in order to solve this or that technical problem using the equation problem solving approach, we need to, among other things, translate the spoken language into the language of mathematics. And here, how do we translate the spoken language of time evolution of population of single cell organisms of chosen fixed type into the language of mathematics? Well, if we are talking about time evolution and we assume that time flows forward, then the spoken language of time evolution and time flowing forward can be captured with the language of mathematics as follows. We can give to the time to the moment of time t, we can give a small increment delta t. And then we can ask ourselves what will be the population of colony of single cell organisms of chosen type at time precisely t plus delta t. Again, how do we convert the spoken language into the language of mathematics in this case? Well, we already know that the number of organisms of fixed and chosen type is x. Consequently, at time t plus delta t, we will also have that number x. And now the question is, how do we relate these two magnitudes to each other, again, in the language of mathematics? Well, here we will go back and look at the variable or magnitude delta t that we had introduced so easily, so to speak. When we said that the time interval delta t is small, we did not really qualify how small is small. Well, in this case, in the first steps, when we work with this material, we keep the exact magnitude or explanation of how small is small a little bit vague. But if we want to get slightly more pedantic, then we can say that the time interval delta t is so small that during that time, none of the organisms in the colony at the moment t captured with x have died out. And initially, to some viewers, that may seem a little strange or unnecessary, but later on, if you stick with this program long enough, you will realize that it's actually not that obvious, it's not that straightforward, and pretty much every statement that we make in order to come up with some mathematical explanation of the spoken language becomes or should become an explicit assumption. As such, we put this assumption in black and white. We give that assumption a dedicated name. Let's say we call it A1. We designate it like so, A1. And again, A1 is the assumption that during the time interval delta t, that is very small. And how small is small? It is so small that none of the organisms in the colony whose size is captured with x of t have died out. Now that this assumption is on the books, we can already construct the symbolic answer to our original question. How can we express the number of single cell organisms in this colony of this fixed type at time t plus delta t in terms of the number of such organisms at time t? Well, based on the assumption A1, we can already claim or convert the spoken language again into the language of mathematics by saying that this number over here will include or contain this number over here. And that inclusion or containment we can designate with the approximate sign. So in other words, when we flip this whole arrangement back, then in words we will say that the number of single cell primitive organisms of the specific chosen type x at time t plus delta t is roughly or approximately the number of these organisms, live organisms, at time t. Next, because we're studying the time evolution of population growth, we need again somehow to convert the spoken language of growth of population into the language of mathematics. And how do we do that? Well, because the phenomenon or the dynamics of the population of colony of single cell organisms is captured with the words increase or growth, as the second assumption, assumption number 2, again, it may feel a little strange to some of our viewers, but eventually, if you stick long enough with the program, this will become second nature. You will realize that you pretty much have to write down all the assumptions that you make while you construct what we will eventually call a mathematical model of a real life phenomenon. Here we book or put it in black and white officially that as an assumption number 2, we think that at time t plus delta t, the number of organisms, the number of live organisms of a fixed and chosen type must be larger than the number of organisms of the same type at time t. And how do we, again, capture or convert that spoken language into the language of mathematics? We do that with the plus sign. We put plus over here. This is how we convert the everyday spoken language into the language of mathematics. And lastly, we come to the final and very important piece that makes the whole thing, so to speak, converge and jive. What is this increment should be? What this increment should be? Here it is important to understand that precisely because we are developing a mathematical model of a real-time phenomenon, this term over here, what we're about to write, doesn't really matter what we will write in this segment and in the consequent segments, is not in general deduced from any higher machinery. That term that we will put over here precisely captures the idea that what we're dealing with is a mathematical model. As such, at first, and again, that step that I'm about to carry out may seem a little bit unnatural to some, but again, let's presume that we're the first humans who are ever studying this. We do not know what lies ahead. We want to see how the things in this respect can work. And as another assumption, as assumption 3, which we book officially, we write it down. We're not lazy. We're writing it down in black and white as an assumption number 3. Here we assume that the increment in the population of colony of this single cell, let's say primitive organisms, during the small amount of time delta t is linearly proportional to nothing but the time delta t that has elapsed since the moment of time t. So how do we capture that assumption? Linearly proportional to. Well, in mathematics, there is a standard mechanism for that. Linearly proportional to translates into a product of at least 2 terms. And in this case, we will write plus k times delta t. That is how we convert the spoken language of linearly proportional to nothing but the time delta t, a small amount of time. We do that exactly like so, where k can be, in general, most of the time, and in many textbooks, this will be called a coefficient of proportionality. And what will be the units of measurement of this proportionality? Well, the units of measurement of this guy should be number of living organisms per unit of time. Because then, in this relation over here, time in the numerator will cancel out with the time in the denominator over here. Cancel, cancel. In the end, what will stand? The only thing that will be left standing is the number of living organisms, and that unit of measurement will square against all the other units of measurements of all the other terms in this relation. Now, what we managed to construct or put together in general is called a mathematical model. So now let us discuss briefly what is a mathematical model of a real life phenomenon. As such, what is a mathematical model of a real life phenomenon in this specific context? In this specific context, a mathematical model of a real life phenomenon is precisely the collection or the set of all the assumptions that went into our description of that real life phenomenon. And as you work along and develop a better feel for how these processes work, you will realize pretty soon that the answer to the question exactly what is an assumption or an axiom that we made in this specific case, then the answer to that question will be it is a statement that later on was converted into some actionable mathematics, and the other way around. If you think that in order to describe this or that model, you said a few words and later on you did not convert these words into actionable mathematics, then probably this is not an assumption. Probably this is not your axiom for this specific model. And conversely, if a statement was made that described this or that real life phenomenon, then that statement was converted into actionable mathematics. That statement is an axiom. And yet conversely again, if we look at the symbolic representation of our model, such as this one, for example, then each and every main component of that symbolic representation can be traced back to the corresponding axiom. For example, in this specific case, this summand, this term right here, seems to be one of the most important, and in the upcoming small number of segments we'll play with the structure of precisely this term. So this specific summand, this term, or the structure of that summand defines or something that makes this model and no other model. In other words, in this model we assume that the incremental change in the population of the colony of a single cell primitive organisms of chosen fixed type that realized during the time delta t is linearly proportional precisely to that small amount of time delta t, and that linear proportional to is a pretty much standard construct in mathematics. It looks like a factor of two products, a product of two factors, I'm sorry, and the number k here is a strictly positive real number. We should add that much, and again, this summand is what makes this model and no other. Now, the process of constructing or a process of putting such mathematical models of real life phenomenon is actually or can be looked at as a standalone and separate job. And for example, back in my time, the college that I went to, in addition to majors, for example, applied mathematics or theoretical physics, also doled out the concentrations in these majors. And these concentrations looked like and were phrased precisely as follows: mathematical modeling of physical processes. Now, in some sense that we understand what is going on, we take off a hat that reads a constructor of mathematical models, and we put on a different hat, a hat that reads perhaps a mathematical inclined thinker, because now we want to take all the material that was given to us by a mathematical model constructor, take it as a given and fixed material. There is no more ifs, buts, maybes. This is it. What we have is what we have. And our job or our mission, should we choose to accept it, is to convert that mathematical model into actionable mathematics or useful mathematics that we can do something interesting and again useful with. How can that be done? Well, that can be done in a number of different ways. Here is one. Looking at and judging by the structure of the arguments and overall the structure of the material that we came up with, one maneuver that comes to mind is the following. We will take this summand over here in this relation and carry it over the approximation sign on its left-hand side, and we will say that the number of single cell organisms at time t plus delta t minus, because this guy was with the plus sign, we carry it over with the minus sign. The number of this species, the number of these single cell organisms at time t is approximately linearly proportional to the time delta t. This is a completely valid and legal maneuver. We did not do anything not reasonable or illegal or invalid over here. That maneuver is understood. Now again, looking at the structure of the arguments of our single variable real-to-real functions x and this guy right here, what can we do? We can divide both sides of this relation through by delta t. Again, remember, delta t, that number, in this case, in general, in mathematics, it could be a positive real number, negative real number. But in our case, because we're studying time evolution, it makes sense that this time delta t over here is positive, but it is not zero, and it is possible to divide both sides of this relation through by delta t. Let us do that. X of t plus delta t minus x of t is approximately k, and this whole thing is divided by delta t. Here, in general, if we're the first humans ever trying to model this or that real-life phenomenon with mathematics, we either invent new mathematics, this is what our ancestors actually did, or we use already the apparatus was developed prior for us. And what next maneuver, what fruitful maneuver can we execute next? Well, here the approximation sign should be understood that it is not only present over here because we're modeling a real life phenomenon with a mathematical abstraction, which is not the reality, but an approximation of it. It also means that the degree of this approximation is better when the amount of the time delta t baked over here becomes smaller and smaller. And mathematically, we will gain the right to replace the approximate sign when we pass to the limit on both sides of this expression. In other words, if we will say that the limit when the time delta t tends to 0, in other words, when we make the time delta t very, very, very small and 0 in the limit, that is the whole idea of this construct, then what will we have? We will have x of t plus delta t minus x of t divided by delta t equal to, here this time again we pay attention carefully, the approximate sign gets replaced with the equal sign because we're taking the limit of both sides when the time delta t diminishes without bound and tends to 0. Here will be the same exact expression, limit when delta t tends to 0 of k. Again, this construct over here is known in mathematics as the first derivative of the function f with respect to its independent variable t, and in a number of ways. Where should I write it? I should probably write it over here. I will put an arrow over here so that you guys understand. A number of ways in which this expression over here can be converted into actionable mathematics, and this will be a show of famous people in the history of mathematics. We can write it as follows: dx or d over t x also can be written as dx over dt, also x dot, also x1 over t, also x prime t over t, also x prime equals. What does it equal to? The limit on the right hand side of the equal sign does not depend on delta t. This is a constant real number, strictly greater than 0. So that by definition is k. And now we have our equation, our expression. And I will explain in a moment what that means. Here to name a few names. This notation over here, d, uppercase dx or uppercase d with the subscript t, is due to the French mathematician Cauchy. He suggested this notation, and it's so why still is they. Dx over dt is the German mathematician Gottfried Leibniz. X dot is what we use in theoretical physics a lot. X with the parenthesized number 1 is a scalable way to designate the first derivative of the function x with respect to its independent variable t, and scalable in the sense that, let's say we want to study the 17th derivative. This notation over here can be adjusted, but this one is definitely not good. And the prime notation over here, this guy and this guy over here, are courtesy of another French mathematician, Lagrange. He suggested this notation. And obviously we see that if we want to study higher order derivatives, that notation with the single prime is not very scalable. But in either way, we will take it that this equation over here can be written simply as x prime. I will designate the variable with respect to which we are performing differentiation. I'll show the independent variable equal to k, and this is the actionable mathematics. That first derivative over here, like this. This is the actionable mathematics that was sought after, and we should all understand how that happened. We made some number of reasonable, we think, assumptions about the behavior of this or that real-life phenomenon. Then we converted these assumptions from the spoken language into its symbolic representation. Then, by performing the manipulations shown over here, we converted the symbolic representation of these assumptions into actionable mathematics, and we managed to construct an equation precisely as the equation problem-solving approach prescribes. Introduce as many variables as needed, construct as many equations as possible, and the third step will be the solutions of these equations, and we will solve this equation in the next segment. Now that we managed to put together a reasonable, or we think a reasonable mathematical model of a real-life phenomenon, where we study the time evolution of the growth of population of single-cell primitive organisms of a specific and fixed type. We converted that model into actionable mathematics. We managed to extract something that is meaningful, or a type of an equation that is generally known as a differential equation. Here we have the first derivative of a function x with respect to its independent variable t, and we know the shape of that first derivative. It's, in this case, k, a strictly positive real number that is a proportionality constant. And the task right now is to solve this equation. Again, this equation can be solved in a number of different ways. For demonstration purposes, I'll show 3 different but related ways. If you know what is going on, you can skip forward. For those who do not know, stick around. What we will do here first is we will multiply both sides of this equation by the first differential dt, like so, equals k dt, and then we will invoke precisely the so-called second fundamental theorem of calculus. When we integrate both sides of this equation over the independent variable t, starting from a time point t0 to time point t on both sides. And let us deal with the right-hand side of this equal sign. It's quite easy. Here we have a constant real number. By the way this mathematical objects to which we refer as integrals, the way they work, this constant can be carried through that sign. So this becomes k times the integral from t0 to t dt. This is a straightforward case. So in this case, this will be k times t minus t0, spelled out further. That means k times t minus k times t sub 0. And what do we have on the left-hand side? On the left-hand side, we have precisely our favorite second fundamental theorem of calculus. And in this case, what do we have? We have precisely the shape of the function x. So on here, on the left-hand side, we have x of t minus x of t sub 0, which is equal to k times t minus k times t sub 0. And for demonstration purposes, we can agree that a synonym for this summand right here, the number of single-cell organisms in our colony at some initial time t sub 0, can be designated with x0, which is another constant real number. Then we will have x of t minus x sub 0 equal to kt minus kt sub 0. And if we carry this term from the left-hand side to the right-hand side of the equal sign, let me write this answer over here so we can come back to it. X of t equals x0 minus kt0 plus kt. This will be our answer that we obtained one way. Let's carefully mark that this is a plus sign, this is minus sign. Essentially what we're saying is x of t is some constant plus k times t. This is our essential result. In a way, our first problem is solved in one way, and in the next segment I'll show how this very equation can be solved in a different way. Using a highly specific mathematical jargon, if in this segment we switch from Lagrange, shown over here, to Leibniz, then we will rewrite the same equation as dx over dt is equal to k. Let me erase the upper boundary from the previous segment, this guy, so there's not confusing. And then again, we execute the same maneuver. We multiply both sides of this equation by one copy of the first differential dt, the Leibniz style. These two first differentials cancel each other out, and we have, what do we have? We have dx is equal to k dt. Again, we integrate both sides of this equation, but this time we carefully note that the left-hand side will be integrated from the initial population size, x0. The meaning of the symbol x0 was explained in the previous segment, till the current value of the size of our population, x. And on the right-hand side, again, we move the constant real number through the integral sign, but we integrate this guy from the initial time moment t0 till the current time t. Again, we move the constant through the integral sign. We integrate like so, k times dt. This is again k times t minus t sub 0. And what do we have over here? Over here on this side, we have the difference x minus x sub 0. That is equal to, let's spell it out, kt minus kt0 x0. And again, we move this constant real number from the left-hand side of the equal sign to the right-hand side of the equal sign. What do we have? X of t is equal to x0 minus kt0 plus k times t. Again, if we compare this expression with the expression that we obtained in the previous segment, then we will see that this is one and the same result. The answer is exactly the same. And in the next segment, I'll show how this equation can be solved in yet a different way. When in the previous segment we switched from Lagrange to Leibniz, what we actually did, we carried out a maneuver that is known in the theory of differential equations as separation of variables. And what does that mean? Well, look, after the Leibniz style cancellation of the first differentials here on this side and the appearance of the first differential on the right hand side of the result, what did we have? Dx, ignore the integral signs for now, dx is equal to k times dt. In other words, on the left hand side of the equal sign we have nothing but a function of x, and on the right hand side of the equal sign we have nothing but a function of t, and that is exactly what it means when we say that the variables were separated. In the previous segment we integrated both sides of this equation in the definite integral sense, but this time, stepping closer to what actually we do in the theory of differential equations, we will integrate both sides of this equation in the indefinite integral sense. In that case, the constant real numbers still can be carried through the integral, and as a result, we will have on the right hand side k times t plus a constant of integration that is associated with the integration of the function that depends on t. And on the left hand side, what we will have? We will have x plus a constant of integration that is associated with the function, with the integration of the function in x. In other words, we will have x plus c sub x is equal to kt plus c sub t. But these two constants of integration are constant real numbers. And in this case, we can, for example, carry the constant cx to the right-hand side of the equal sign. And what will we have? X is equal to kt plus c sub t minus c sub x. But this is a constant, so we can rename it again into k times t plus a constant. And how do we recover the value or a synonym or another name for this constant c? Exactly, we do what is a tradition in the theory of differential equations. We use the so-called initial conditions. At the time t that is equal to t sub 0, we have k times t sub 0. We simply take this formula or this result over here, and instead of x, we insert the value of that function at the time t sub 0. T sub 0 shows up on the right hand side. The constant remains unchanged, c. And again, if we agree that this is a synonym for x sub 0, then what do we have? We have x sub 0 is equal to k times t0 plus a constant of integration. And from here, what do we have? From here, we have it that c is equal to x sub 0 minus kt sub 0. That maneuver is nothing but our proverbial middle school arithmetic. And now we take this guy and we put him back in this expression. And what do we have? Kt into this expression. No, not in this expression right here. We put it here, and what do we have? Kt plus x sub 0 minus kt sub 0. Again, if we rearrange these summands slightly, we still have exactly the same result. In other words, let's rewrite it to be explicit and careful. X of t is x sub 0 minus kt sub 0 plus kt, which is exactly an expression that we obtained in the previous two segments. And in some sense, this problem is solved. We now created a model which is linear in some sense. And one more thing we need to discuss about the whole process of modeling is that in the title of the very first segment in this episode, you saw something that said continuous one-dimensional models unlimited resources, linear growth, linear solution, population growth, and continuous over here. What does it mean? Of course, we need to understand when it comes to counting the numbers of, for example, people or live organisms, single cell primitive organisms, nothing is really continuous. And whether is the whole situation is Riemann, let's say, integrable to begin with is also a totally different question. But because this is a model, we take our numbers, the numbers x and the numbers, this number is x, and the number, where is it? The x0 over here. We take these numbers to be so large that the increments that we talked about in our model, remember where we had the term x times delta t, this increments compared to the total number of the single cell organisms in that colony is much smaller. That increment is much smaller, and in that case, approximately again, we can take it that the functions that we're dealing with are integrable. They possess the first derivative at least. They can be integrated and so on. And now that we understand how the situation when the numbers of population or certain population grow, we can look at the situation where the number of certain items diminishes with time. In this segment, instead of looking at the situation where the population of certain numbers grows, we will look at the situation where the population of certain numbers decreases or diminishes with time. Because I was slow and thorough in the previous segments, I will not be as slow and as thorough in this segment. And if you fast forward it here and you feel that you are lost, then that probably means that you should go back and work your way through the previous segments. Now, experimentally, it has been proven that the ratio of the radioactively decayed atoms during a unit of time to the overall number of non-decayed atoms is a constant that only depends on the type of atoms, and that constant is known as the probability of decay. Let me write it down maybe over here. It's designated with omega. We will use it maybe sometime. We'll definitely use it sometime later. But again, because this time the number of the atoms that were not radioactively decayed diminishes with time, what type of mathematical model we will construct? Well, again, we will go through pretty much the same steps through which we went in the previous segments, and we will write down pretty much the same relations that will use the same variable x for the number of not radioactively decayed atoms at the time t, and the number of the atoms that did not decay yet after a small time interval delta t has elapsed will be this number of the non-radioactively decayed atoms at time t. But this time, because the overall numbers diminish with time, again, how do we translate the spoken language into the language of mathematics? In the previous case, when we studied the time evolution of a certain colony of single cell primitive organisms that grew over time, we used the plus sign. Now our numbers at hand diminish over time. So we translate that spoken language into the language of mathematics using the minus sign. And again, as a first rough approximation of reality, we'll steal the same constant real number k times delta t, again as a working hypothesis, as an assumption, or as a working axiom. We will, for now, investigate what will happen if the number of atoms that did radioactively decay during that small period of time delta t is proportional precisely to the first power of that time interval. And now that we put together our model, we want to extract actionable mathematics from it. Here the manipulations are exactly the same. Let us go over them in an expedient fashion. X plus delta t minus x of t is approximately minus k times delta t. Again, the structure of the material that we have at hand suggests that we divide this whole thing by delta t. Divide by delta t is approximately negative k. Then we apply the limit when delta t tends to 0 on both sides. We obtain the expression which says that the limit when delta t tends to 0 of x of t plus delta t minus x of t over delta t is equal to, again here we transition from approximately equal to equal sign, the limit of negative k, carefully, negative k when delta t tends to 0. And we know that the formation on the left hand side is the first derivative. We know about Cauchy, we know about Leibniz, we know about theoretical physics, we know about Lagrange. This is a constant real number, which is negative k. Here we have our first derivative of the function x of t, so we will write our equation like so. X of t is equal to minus k. In the previous segments, I explained how to solve this particular ordinary differential equation of order 1 of t over here. I will not go over the same details. If you feel that you are lost, then please work your way through the previous segments. Here we do again the same thing. For example, we can separate the variables, integrate both sides, introduce the constants of integration, merge two constants of integration into one, determine the value of the constant of integration from initial conditions, and basically once we go through all these motions, we will discover that the result for the number of non-radioactively decayed atoms as a function of time t will be actually similar in structure as over here. It will be x of t equals x0, whereby x sub 0 we will designate what? The number of non-decayed atoms at the time t0. And we will realize that mathematically all we need to do is replace the value of k in the previously obtained result with the value of negative k. So here we will have the result plus kt sub 0 minus kt as yet another result. And now that we developed a little bit of a feel for this type of problems, we more or less understand how these things come about, how these things come to life, we can look at the original problem in which we investigate the propagation of information through people over time. Wonderful. Now that we're beginning to develop a better and better feel for how to deal with this specific type of problems, we can address our original problem and go back to the question about the effectiveness of propagation of information through people over time. What do we do over here? Well, again, by analogy with the previously conducted analysis, we introduce the variables. Here, this time we will call x of t will be what? X of t will be the number of people who know about a product P that was advertised once by company C, and so on. And how do we extract actionable mathematics from this humble beginnings? Well, we will again study the behavior of the number of the people who know about the product P after a small amount of time delta t has elapsed from the time t. And again, all these processes unfold after the advertisement was carried out. And here, what do? Well, we hope that the number of people who know about the product P grows over time. And how do we translate the spoken English of grows over time into the language of mathematics? Well, first we put the plus sign. We already know that much. And again, here, as a first rough approximation of reality, we will assume, and we know that this assumption becomes essentially a model that makes this model, and no other model, will be linear proportional only to the time that has elapsed since the moment of time t, or linearly proportional to the time interval delta t. Again, some of our viewers may feel somewhat uncomfortable why Roman is doing this. This doesn't really make much sense. Roman should be doing something else. This is a perfectly valid observation, but there is a method to the madness. Please bear with me. I have a point to demonstrate over here. So here, now once we obtain this mathematical model for our problem S2M21, again, we move in exactly the same fashion forward as we moved in the previous segments. If you see what is going on, then you can again skip this segment and go to the next one. But here we will quickly observe that again, we will move this summand from the left-hand side to the right-hand side of the approximate sign and obtain xt plus delta t minus x of t is approximately k times delta t. And what do we do next? We divide both sides of this relation through by delta t, and we can do that because delta t is not 0. By doing so, we invent new mathematics that is called differential calculus. We apply limits to both sides when the time interval delta t tends to 0, and we obtain x of t plus delta t minus x of t on the left hand side. And here we replace the approximation sign with the equal sign. Limit of k this time when delta t tends to 0 and tends to 0 on both sides. Over here we obtain the first derivative of the function x with respect to the variable t. This is equal to k because this limit equals to precisely k. This is a constant real number strictly greater than 0, and we again obtain exactly the same differential equation that we obtained in the first case. But now we have to be cognizant of the fact that in the first problem that we considered, this summand over here corresponded to what? To the number of offsprings, each and every living single cell of which was produced by that cell with a certain probability. In the second problem, we didn't have the plus sign, we had the minus sign, but k delta t back then represented what? The number of radioactively decayed atoms. In this problem, what does the summand k delta t represent? In this problem, the summand k delta t represents the growth or the number of people who learned about a product P advertised by the company C once. So this summand over here is the positive increment in the number of people who learned about the product P. And the solution of this equation over here, I will not go over it again. If you feel that you need to go over it one more time, please go to the previous segments where we explain how to solve this equation in 3 different ways. But fundamentally, nothing changes over here mathematically. We see that mathematically, this problem and the problem that concern the time evolution of the population of single cell organisms of a specific type are mathematically the same. They're not distinguishable. As far as mathematics is concerned, it's one and the same equation that describes both processes. And the equation and the solution that we obtain for our original problem in our first approximation is exactly the same as the first one. It is shown over here. And now I will address some of the questions that you may have, and we will discuss certain pedantries as they relate to the work that we just carried out. Now let us address some of the questions that you may have raised during our previous discussions. First, in order to be good theory of differential equation citizens, after we solve a differential equation, then in theory we need to analyze it to death and utter the words such as direction fields, integral curves, isoclines, asymptotes, stable and unstable, attractive and non-attractive solutions, various regions where the solution is valid, where it's not valid, and so on. But we will not be doing in this episode because the emphasis of this episode is not on the mechanics of the theory of differential equations. The emphasis of this episode is to show how the equation problem solving approach can and does dovetail into grown-up or serious mathematics, and there you go. Especially in this episode, we want to concentrate on the transition from the first step of the equation problem solving approach, introduce as many variables as needed, towards this second step, solve as many equations as possible, because that transition is what becomes the heart and the soul of the process to which we refer as a mathematical modeling of real life phenomenon. We know that a mathematical model of a real life phenomenon is basically the sum total of all the assumptions or axioms that went into description of this phenomenon, and each such assumption or each such statement was later converted into actionable mathematics, and some result was hopefully derived from it. We should remember that a mathematical model of a real life phenomenon is never the reality, but a certain approximation of that reality. And where does this approximation of reality come from? Well, usually we construct such a mathematical model of real life phenomenon that we usually, again, can handle mathematically. Of course, we know that neither the mother nature nor the mathematics is under an obligation to dole out special intellectual flavors for us. If we cannot handle the underlying mathematics, it's on us, it's not on Mother Nature. But in general, the assumptions that we make during the construction of mathematical model usually tilt or bend mathematics our way or in the way in which we can handle the result in mathematics. So let's say a model, our model, produces something that looks like this, but the reality looks like this. And somewhere our model intersects with reality, but somewhere it does not. But one thing that we all should be on the same page in regard to is the following very important idea. Yes, the source of an approximation of reality is this set of assumptions. That is correct. But once the sum total of all the assumptions is folded into a model, the output of that model is an exact solution. As such, with mathematical modeling of real life phenomenon, what we get on the output of the process is again an exact solution of an approximate problem. And that is hopefully now clear what I mean by saying that an exact solution of an approximate problem is an output of a mathematical model. And what that means is that the approximation of reality comes from the assumptions that we bake into the description of this phenomenon. These assumptions usually lead to mathematics that we can handle, and precisely there sits the discrepancy between the real life and our model. But regardless of all that, the solution of the model is exact. For example, when we wrote down the equation, the ordinary differential equation of order 1, x prime t over t equals something, the solution of that equation was exact. We produced it in a manner where we didn't cut any corners. So far, so good. So now it is actually a good idea for you guys to print out this little idea on a piece of paper in large font in many copies, hang it all over your house, so every time you go upstairs, go into the bathroom or go walk into your bedroom, you see this sign. And this is actually also how theoretical physics works, except that of course in theoretical physics We do not just study any real life phenomenon, we study very specific real life natural phenomenon. But overall, the computational program of theoretical physics is to produce an exact solution of an approximate problem. Now let us finally decipher the words that we saw, that I showed you guys at the beginning of each segment. Continuous, one-dimensional model, unlimited resources, linear solutions. What does continuous mean? Continuous means that in this model, we take it that all the magnitudes that we study vary continuously. Of course, we should all understand this is an approximation. Even in many cases, we can take that the time t varies is varying continuously, and its variance is modeled, let's say, with real numbers. When it comes to the number of living organisms of certain type, or to the number of people, of course, that number does not vary continuously. But in our model, the behavior or the approximation of being continuous is the better, the more these numbers are. One-dimensional, I already explained in the previous segment. The dimensionality of a system of differential equations comes from the number of unknowns that, or number of magnitudes that completely describe this or that system, and a direct analog of the dimensionality in the theory of differential equations in theoretical physics is a degree of freedom. And in this case, we can completely and fully describe the behavior of the system under study with just one magnitude. We refer to it as x. Hence, all our models are one-dimensional. If we were studying this or that real-life phenomenon and we realize, gee, we need two x and y, we need two magnitudes in order to completely describe the behavior of the system, then that model will be two-dimensional. If we realize, gee, we need three variables, x, y, and z, in order to completely and fully describe the behavior of the system, that would have been a three-dimensional model, and so on. Unlimited resources. In all our manipulations that we have done so far, we quietly assumed that the numbers at hand are available or grow without any limitations. And how do they grow? They grow linearly, because essentially these two solutions over here, we can write it down as follows. X behaves like plus minus t. Again, over here, if we were to be good citizens of the theory of differential equations, we need to talk about direction fields, integral curves, and so on. I do not want to get bogged down with these details. Fundamentally, our models produce linear solutions where all the numbers at hand depend on the time t linearly. Now let us step back and take a look at our solutions with a sober attitude. How realistic, or how well does our model describe reality over here? How big is the discrepancy between what our model will predict and what we will observe in reality? Here, our solution, okay, on the one hand, again, if we're taking a sober look, on the one hand, we do have a reason to celebrate, because we took a real life phenomenon, we said a few words, and we did manage to come up with some reasonable mathematics that we can handle. That is a big deal. That is a sizable achievement on its own. But on the other hand, how realistic is it that the, for example, number of single cell organisms will grow with time linearly, or that the number of radioactively decayed atoms will also grow, or diminish this time, diminish linearly? And how realistic is it that the number of people who know about a product P will also grow linearly with time? That doesn't seem to be too realistic, because, for example, we kept saying that this colony of single cell primitive organisms is of a fixed, certain fixed type. And how did we use this information in our solution? Well, we didn't really use it, and we will address precisely that issue in the next segment. Now that we're all on the same page, and because you were paying attention and you will be following along with every consequent segment, I will move you a little bit in a more and more expedient fashion. Now we go back to the problem where we investigated the time evolution of the population of a colony of cells of a specific chosen and fixed type, and we want to make our model slightly more realistic. And how can we do that? Cutting to the chase, we come back to the structure of the summon to which I referred in our first segments, and now this is exactly the place where we concentrate our attention. When we say that with certain probability, each and every living single cell of a fixed type can produce an offspring, we say that during the small time delta t, how many such offsprings our colony can produce. Well, let's step back for a second and think about how we will translate this spoken language into more precise mathematics. What does make this colony of cells this specific chosen or fixed type? Well, I'm not a biologist, but apparently a certain genetic and biological material that makes this specific chosen fixed type of primitive organisms what they are. Consequently, when they produce an offspring, they produce an offspring that possesses that specific genetic and biological material that makes this offspring of this type and of no other type. Consequently, and again, it is important to understand that because we're constructing a model, this next observation is not produced from any higher mathematics. This is our assumption, and that is exactly what goes on the books, and that is exactly what will make this model, which will be different from the previous model. Hence, we argue over here that during the time delta t, the number of offsprings that can be produced by each and every organism of this type with certain probability will be proportionate not only to the time, but to the size of that colony itself. So let's think about it. What does that mean? It means that only the organisms of this type can produce offsprings of the same type. So that much should make sense. So how do we change the structure of this term over here? Well, we multiply this guy by the size of the colony at the time t. This is the maneuver that goes on the books as a separate assumption. This maneuver is what changes the structure of this summoned, and this is the maneuver that gives a new name to the model that we will obtain in the end. But again, we consciously have to record this observation as an assumption. And now what type of manipulations follow? Well, if you've been following all along, you know that you know what's coming next. We subtract this term, again, this summand, from both sides of this relation, and we obtain x of t plus delta t minus x of t approximately is k. I will swap these two factors. I'll write x of t delta t. These are real numbers. Real numbers commute under multiplication. And now we divide this relation through by delta t. Delta t is not 0. We can do that. Again, we remember that in the process we're discovering new mathematics. Okay, x of t. The mathematics is called differential calculus, delta t, and in order to replace the approximation sign with the equal sign, we apply the limits to both sides when the time delta t tends to 0, and again, it should be evident that as we decrease the size of this time interval, we overall improve the accuracy of our model, of the numbers that we hope that we will witness. And as we tend this number to 0, we generate a construct called the limit. We produce a first derivative and so on. But what we have here is x of t plus delta t minus x of t 1 over delta t equal. Now it's not the approximation sign, it's the equal sign. same limit, delta t tends to 0, of what? K times x of t. This is the limit. We take the limit of this expression. Now here, actually very little changes with respect to what we did in the previous segments. What we have on the left-hand side is the first derivative of the function x with respect to its independent variable t. So we still capture this equation as x prime t over t. But now what do we have on the right-hand side? As far as this expression is concerned, there is no delta t over here. So the limit of this expression is that expression itself. So what we have here is k times x of t. This is our result. And in the next segment, we will discuss how this particular ordinary differential equation of order 1 can be solved. In the lightning round, Isaac Newton got actually pretty good at solving this and similar type of differential equations by using the mathematical objects to which in modern times we refer as the power series. In other words, let's say again, for simplification purposes, for demonstration purposes, we take this differential equation, forget about the constant coefficient of proportionality, k. Let's say we have the equation that looks as follows. The first derivative of x is the function of x itself, and as another simplifying assumption, we take it that evaluated at the point 0, this function comes out to be 1. Here, Isaac Newton made an assumption, and in some sense, this is also how mathematics works. We do not really know what lies ahead, but we make a bold assumption. Here, let's say Newton assumes that the solution of this differential equation is a function that can be represented as a power series in its argument t. In other words, the function x at the point of t can be decomposed into this infinite series, a0 plus a1 times t plus a2t squared plus a3t cubed plus a4t to the fourth, and so on in like manner. But now what do? You see, this bright idea gives us tactical advantage. We know how to differentiate a polynomial in a way. We know how to differentiate each such function shown over here as a standalone term. And once we differentiate such a function, we get a0 disappears, and instead of a1t, we get a1, 2 a sub t sub 2t, 3 a sub 3t squared, 4 a sub 4t to the third, 5 a sub 5 times t to the fourth, and so on in like manner. And what do we do now? Well, we now go back and we use this equation right here. We know that the first derivative of the given function with respect to t is the function itself under this initial condition. And now we equate. If these guys are equal, so must be this and this and this and this and this and so on, because the powers over here are the same. You see 3 and 3, 2 and 2, 1 and 1, nothing and nothing. And in the manner as explained over here, we recover the values of the coefficients. But here we face a converse problem that, for example, says that once we know the names for the coefficients, we need to roll this infinite series into a function whose name we know, and it's a different story. And maybe in the future, that method is actually too beautiful to be winged. I will put a dedicated episode which explains exactly how this type of differential equations can be solved using the idea of power series. Unlike Isaac Newton, the Swiss-born mathematician and theoretical physicist Leonard Euler had a different idea. That is, Euler suggested that instead of looking for an exact solution right away, we approximate a solution of a differential equation, which, lo and behold, can be interpreted geometrically as a so-called integral curve. Not with the integral curve itself, but in a certain approximation as a polygonal line or an object that is represented by a sum, if you will, of line segments that are connected end to end. And lo and behold, in this specific case, it can be shown that again, as an approximation, the solution x can be represented as the value at initial point x0 times this formation over here. And in order to replace the approximation sign with an equal sign, what do? Again, modern students of mathematical analysis instantly recognize this very famous numerical sequence. What do we do here? We take the limit of this formation when n tends to positive infinity, and we get the solution that is very famous also by now. And again, because this idea is very beautiful, I do not want to wing it in the future. I'll probably put together an episode that goes into the details of this solution. But meanwhile, we will cut to the chase and we will use the machinery of the modern theory of differential equations in order to solve this equation shown over here. As you work with differential equations that model a real-life phenomenon, you will quickly realize that the better or the closer your mathematical model describes this or that real-life phenomenon, the more complicated the structure of the underlying differential equations gets. And eventually, in such a mathematical modeling of real-life phenomenon, you will reach the point where your differential equations cannot be solved using the elementary functions. Some of these differential equations can be solved using the so-called special functions, and by now these special functions are studied and understood so well that these special functions may as well be called a new class of elementary functions. You will meet a lot of these functions if you take a course on the equations of mathematical physics, for example. The equation that we deduced in this episode, the equation that I wrote on this side of the board, the first derivative of the function x of t over the variable t that is proportional to the value of the function at that specific point, is not that complicated by the way things go, because even more differential equations that describe a certain real-life phenomenon pretty good cannot be solved even with the special functions, and we try to solve these equations numerically. But the equation that you see behind me on the board was apparently first introduced by the English scholar who goes by the name Thomas Malthus. He lived during the time period that you can see on the board over here. And judging by the examples that you guys saw a few seconds ago with the attempts of Isaac Newton and Leonard Euler to search for the solutions of this equation, this equation plays a fairly important role in mathematics, because precisely the ways in which Isaac Newton and Leonard Euler were looking for the solutions of this equation led to the development of new serious and beautiful mathematics. And precisely because our mathematical ancestors, or the mathematicians who came before us, gave us this powerful mathematical apparatus, we can solve this equation these days in about 30 seconds or so. And the way we will do it is by using the same idea that we saw in the previous segments, and that idea is called separation of variables. We also know the program that lies ahead. We switch from Lagrange to Leibniz. We write our differential equation in the following form: dx over dt is equal to k times x. I will drop the designation of the independent argument over here in the consequent manipulations. We'll all understand that x is a function of the independent variable t, which is time, and let's say we measure time in days, for example. Now we multiply this equation through the Leibniz style by one copy of the first differential dt, and we obtain dx over dt times dt equals k times x times dt. This maneuver should be understood by everyone. We cancel out the first differentials on the left-hand side of our equation, but the first differential dt stays on the right-hand side. So we obtain dx is equal to k times x times dt. Are our variables separated at this stage of our solution? The answer is no, they're not, because to the differential dt we have attached a factor that has nothing to do with t, x. So how do we separate these variables in this case? Well, we divide both sides of this equation by this here, one copy of x, and we obtain dx over x is equal to k times dt. And now we managed to separate the variables in our original ordinary differential equation of order 1. And by doing so, we prepared this equation for integration. Now, we will carry out the integration of this equation in the indefinite integral sense to be closer to the spirit of the theory of differential equations. As such, we integrate both sides of this equation in the indefinite integral sense. And what do we have? We have, let me write it over here, indefinite integral of dx over x is equal to indefinite integral of k dt. That maneuver should be understood. And now the integrals, the indefinite integrals that we're dealing with in this case are quite straightforward. They're easy to deal with. The first integral, the integral on the left-hand side, comes out to be natural logarithm of absolute value of x plus a constant of integration that is associated with the integration of the function in x. And that is equal, we know we can move the constant through the integral sign over here. Integral of dt in the indefinite sense becomes t. So on the right-hand side, we obtain k times t plus a constant of integration that is associated with the integration of the right-hand side with respect to the dummy variable t. We have two constants of integration. And due to the way in which the logarithmic function is defined, to be completely pedantic about it, we need to specify what? We need to specify the interval over which this indefinite integration is valid and legal. So this interval goes from negative infinity to 0 on this interval, or on the interval from 0 to positive infinity, like so, because again, via the definition of the logarithmic function. But in our case, don't forget, what does the function x of t stands for? The function x of t stands for the number of primitive organisms of a specific type, because these numbers are always strictly positive, let's say real numbers. We can drop the designation of the absolute value of the underlying function x, and from now on, once we understood that we will be working with this interval right here, so we will say that x from now on is less than positive infinity and greater than 0, we will make the following maneuver. We will carry this, let's say, constant of integration to this side, and what will we have with the designations that we agreed on? We will have logarithm of x equal to k times t plus constant of integration t minus a constant of integration x. But a difference of two constant, let's say, real numbers is yet another constant real number. So we absorb this difference of two constants into yet another constant. And what do we have? Let's write it over here. Logarithm of x is k times t plus a constant c. So now the question is, how do we recover the synonym for the constant of integration? In order to recover the synonym or another name for the constant of integration, see, we use the initial conditions, and in this case we will take it that agree that at the moment of time t0, k times t0, we know what this time is. It could be 0, it could be non-zero value. The population of our colony of primitive cells will be x0. So far so good. In other words, we will say that x of t sub 0 equals x0, as long as we understand that this is our agreement and this is where the symbol x0 came from. Now we have, what do we have? What is this called? Well, befitting the study of the problem-solving approach called equation, this is yet another equation. This is a linear equation in C. Easy to solve in this case. C is equal to logarithm of x0 minus kt0. And now that we know the name of this constant, what do we do with it? We insert this guy back over here and we replace this guy. What do we have? Logarithm of x, the natural logarithm of x, is k times t plus logarithm of x0 minus k t0. That maneuver should be understood by everyone. We simply took the right-hand side of the expression for c and put it on the right-hand side of this relation over here. Now we move the logarithm of x0 to the left-hand side of the equation. Logarithm of x minus logarithm of x0 is kt minus kt0. Using the property of the logarithmic function, we can rewrite this which way? I will hijack the same real estate because I don't have much, but you understand that you write a new line in your notes. This becomes a plus and this becomes -1. So the symbol x0 is raised to the negative first power. And then we use one of the defining properties of the natural logarithm. And by the way, by doing so, we're also dealing with a certain type of group isomorphism, for those who are interested. So we combine this sum into a product. Log x over x0 is equal to kt minus kt0, and then we potentialize this expression. In other words, we put the base of the natural logarithm in such a way that these expressions become the powers of the natural logarithm over here. By definition, this is what? This is x over x0 equal to e to the power minus kt0 times e to the power kt. Here with this maneuver I used another fundamental property of the exponential function, and I split the exponent that has its power as a difference of two terms into a product of two exponents, like so. That maneuver should also be understood. This is nothing beyond early high school mathematical program. And now we isolate x on the left hand side and we write down our answer. X of t is x0 times e to the power, what is this guy? Negative kt0 times e to the power kt. We realize that we deduced this solution based on our agreement and understanding how indefinite integration works pedantically. All indefinite integration must be accompanied by the specification of the interval over which this indefinite integration can be carried out. Doesn't really matter. We have a logarithm or whatever. Arctan, arcsine, whatever the functions we're dealing with need to specify the intervals. Here we specified both. We agreed on this interval. From this, the shape of the function followed, and we obtained our result. So in another way, because let's think about this a little bit. X0 is a constant real number. K is a constant, strictly positive real number. T0, again, is a constant, and in this case, strictly positive real number. It means that this construct over here is also a constant. And fundamentally, what we deduced with this equation is the following. The shape of the function that models the time evolution of population growth of single-celled primitive organisms of a specific chosen fixed type under all the conditions that we agreed upon earlier is given by a multiplicative constant whose value for now doesn't really matter for us, and the exponential function kt. This is our result that we obtained in a public setting. I hope that everyone was able to follow every step of the way. If you have any questions, then don't be shy. Ask these questions in the comment sections to this video. But now that we understand how this solution was obtained, we can take a look at the problem of the radioactive decay of atoms, in which case the population, instead of growing, diminishes with time. Now that we understand how we put together a mathematical model of the time evolution of population growth of primitive organisms, I will cut to the chase when it comes to a mathematical model of radioactive decay of atoms that we discussed in the previous segments. Here, we will compare what we need to do with what we have done previously. In the mathematical model of the time evolution of population growth, the structure of the interesting term, which I advertised at the beginning of this episode, had the following shape. The linear proportionality of the number of offsprings in this colony was captured with this term, k times delta t, and we agreed that because only these single-cell organisms possessed a specific genetic and biological material, then only this colony captured with x of t can produce some number of offsprings. When it comes to the radioactive decay of atoms, what will the structure of this interesting summon be? Well, first of all, we know that the atoms radioactively decay, so their population, instead of growing, diminishes with time. That's how we will translate the spoken English of diminishes with time into the language of mathematics. Well, here we will, instead of the plus sign, we will put the minus sign. From the population of non-decayed atoms, we will subtract something. Something what? Well, we'll use the official probability of radioactive decay, omega, times, again, there will be time delta t, which stands for the number of atoms that will radioactively decay during the small time interval delta t. And again, remember that this probability of decay is a constant that is only dependent on the type of atoms. And that means that only this population of non-decayed atoms can possibly decay in this specific fashion as captured with the symbol over here. That means that it is reasonable, or in some sense natural, to assume, again, this is a hypothesis, this is a hypothesis, this is an axiom, and this is an axiom, or an assumption, if you will. It is natural to assume that the amount of radioactively decayed atoms that will be produced during the time interval t will be linearly proportional to the size of the current population of non-decayed atoms. So here we will write exactly again times x of t. That is how we introduce the term x, or the current value of the function x at the time of t, and the rest what follows is exactly the same. You already know what will happen next. We construct the difference by subtracting this term from both sides of this relation. Minus x of t will be proportional to negative omega x delta t. We divide this relation through by delta t. If you know what is about to happen, then you guys can skip this and fast forward to the next segment. Delta t is approximately negative omega x of t. We know that the approximation sign captures not only the fact that we're modeling real life phenomenon with mathematics, but it captures the fact that the approximation here is generated by this finite size of this time interval. As we make the time interval smaller, our model becomes, we think, more and more precise. It matches what happens in reality closer and closer, and we replace the equal sign with the we replace the approximation sign with the equal sign if we pass to the delta t tending to 0 limit. In this case, delta t tends to 0 equal to, see, right here, we pay attention. This is the courtesy of limit, the notional limit. Negative, limit of delta t's tending to negative omega x of t. That much. What we get over here is the wonderful invention. This is the first derivative, so the equation that we obtain is the following. X, the first derivative, the function x of t with respect to the variable t, is equal to, here nothing depends on delta t, so this becomes negative omega x of t, multiplication sign. Again, this structure, the structure of this differential equation is pretty much the same, essentially the same, modulo the sign in front of the multiplicative constant. So if this solution was associated with this equation, then with the equation that essentially reads the first derivative of x is equal to negative omega times x, then how do we cook up the solution of this differential equation based on the solution of this differential equation? Well, in the solution of this differential equation, we uniformly replace k with negative omega. Voila, done deal, problem solved. So here, in this case, what will we have? X of t is equal to x0 times e to the power omega t0 times e to the power negative omega t. That much we understand. Again, a constant real number which represents what? This is a constant real number that represents, or in this case will be counting number, that represents the number of non-decayed, non-radioactively decayed atoms at the moment time t0. Omega, the probability of radioactive decay, is a constant, t0 is a constant, x0 is a constant. The whole construct over here is a constant, so we can essentially write x of t is equal to some multiplicative constant times e to the power minus omega t. This is our solution of this equation. And now that we understand how this solution unfolded in the case where the population of something diminishes with time, we can come back to the discussion of the solution of our original problem S2M21. Coming back to our original problem, in which we're trying to study the effectiveness of advertisement from the standpoint of mathematics, we reason that the number of people who know about a product P that was advertised by company C once will grow over time. And that is why, by analogy, and that is why we went through all the previous exercises. Thus, by analogy, we come to our previously solved problem in which we studied the time evolution of population of primitive organisms. Here, however, we need to understand and make peace with the structure of the new summand, which I kept the same from a couple of segments ago. Why would the structure of this interesting summand that I advertised at the beginning of this episode will be as shown over here and essentially the same as in the population growth problem? Well, by analogy again, if only this group of living single cell primitive organisms that possesses this specific genetic material and biological material can produce the offsprings with that genetic and biological material, and in some sense also by analogy with the radioactive delay of atoms, because only this group of non-decayed atoms can decay in this specific fashion captured in this probability of decay. Here, only this group of people who knows about a product P can possibly propagate that information about that product further during the time delta t, and that is why the structure of this summand, even in the information propagation problem, looks exactly as shown over here. To give a descriptive example for demonstration purposes, let's say we have 10 people in the room. 7 people in the room have no idea about the product P, and 3 people do know about this product P. 2 guys over there talk to themselves in the corner. They don't care about anything else. 1 person over here who knows about this product P walks over to the group of 7 people in order to talk to them. He or she is an outgoing person, and they begin talking to that group. Out of this group of 7 people who have no idea about this product P, 4 people don't care. They walk away. 3 people remain. Among the group of 3 people that remain, 2 really do not listen. They don't care. Only 1 person does listen, does pay attention, and consciously absorbs the information. Oh, a company C has this new product P. Wonderful. Let me see what's going on. Bam, the information jumped from 1 person to another. So fundamentally, what we are saying with this model of the effectiveness of advertisement is that the larger the group that knows about the product P now, the larger will be the positive change or the increment in the number of people who will know about the product P during this time delta t, the change that will be realized during the small time delta t. And conversely, the smaller the size or the body of the group of people who know about the product P, then the smaller will be the incremental change in the number of people who know about this product P, and that change is realized during this small time interval delta t over here. Once that is understood and digested, now we see where this factor in this summand come from. It seems to be, again, natural and reasonable to assume that the more people know about this product P now, the more people will learn about this product during the next incremental time interval delta t. This becomes, again, an assumption. We book it. This gives birth to a new model, a new mathematical model that is different from all the other previously constructed mathematical models, and we understand how the solution will unfold. I will not go through exactly the same motions. You already know what will happen. Construct the difference, divide by delta t, take the limits on both sides as delta t tends to 0, obtain the first derivative of x with respect to t on the left-hand side, obtain this product over here on the right-hand side. So effectively, we'll have exactly the same thing. Ordinary differential equation of order 1, first derivative of x is equal to k times x, let me be neat over here, times x of t. And because notice that descriptively, this problem that deals with the effectiveness of advertisement is mathematically equivalent to a problem that is descriptively different, the problem that studies the time evolution of population of growth of primitive organisms. Then the solution of this equation will be exactly the same. We will have exactly the same result, which will be expressed as a multiplicative constant times the exponent raised to the power of kt. Now that we constructed this model, we step back again, and now we inquire how realistic the new mathematical model of the same phenomenon is, and we will have this discussion in the next segment. Here we have a small reason to celebrate because we managed to say a relatively small number of words and come up with a reasonable mathematical model of a real-life phenomenon. We further were able to extract mathematics that came out to be legal, reasonable, and valid, and also interesting. But on the other hand, we take a sober look at our model and inquire how realistic our new model is, or how well or how truthfully does our new mathematical model describe this or that real-life phenomenon. To be perfectly clear, our new model is still continuous, it is still one-dimensional, it still uses unlimited resources, but now this model outputs solutions that are essentially exponential in their nature. In the first and the third problem, in the problem where we studied the time evolution of population growth of primitive organisms, and in the problem where we studied the effectiveness of advertisement mathematically, the solutions represent exponential growth. And in the second problem, where we studied the process of radioactive decay of atoms, that solution portrays essentially exponential decay. Now, if we want to discuss a graphical representation of any solutions of differential equations, then in order to be good theory of differential equations citizens, we need to frame our discussion in terms of the so-called integral curves. And these so-called integral curves have a number of interesting properties. For example, one such property says that any two integral curves that represent a solution of one and the same differential equation over the same region, they either do not intersect. For example, if there is a second solution that is represented graphically here, it will run closely to the existing one, but it will never intersect one. Or in the other case, that integral curve will completely coincide with the second one, like so. And in a far corner of mathematics, or seemingly far corner of mathematics, called the theory of groups, we have a phenomenon that actually described in exactly the same way. For example, any two cosets of any group with respect to any subgroup of the pairing group either do not intersect or coincide completely. So the description over here of these two features or properties are exactly the same, except that in the first case, when we say two geometric objects intersect, we mean geometric intersection, as shown over here, for example. And in the case of the theory of groups, we of course mean set theoretic intersection, or the number of elements that two sets have in common. In the first case, that set is either the empty sets, when we say that the two cosets do not intersect, or these two cosets coincide completely and their elements match one-to-one. But I do not want to get bogged down in the weeds of the theory of differential equations over here. This is not the point of this episode. The point of this episode is to show how the equation problem solving approach can help us construct reasonable mathematical models of real life phenomenon. And let's say here we just look at one partial graphical representation of one solution of this differential equation that describes the exponential decay of radioactive atoms. And here, in general, from the perspective of overall theory of differential equations, one question that is quite popular and very important, again, in overall theory of differential equations is the following: how will the solution or solutions of our differential equation behave in the limit when the independent variable of that solution grows without bound, in our case, when time t tends to positive infinity. Mathematically, since we know, or symbolically or analytically, if you will, since we know the shape of the solution, we can compute the limit of our solution. I threw out the multiplicative constant over here. It's not essential for this discussion, but fundamentally, the value of this limit is 0. That means that asymptotically over time, that solution reaches a stable state when the, for example, given matter virtually all decays. And in this case, if we inquire how well our model constructed over here portrays or describes reality, then it seems that we do not have a lot of good reasons to worry about this mathematical description of a real life situation, because things seem to behave reasonably as we expect given some initial number of radioactive atoms. Then if that number or that population of radioactive atoms is left to its own devices, if we're willing to wait long enough, then eventually we will see smaller and smaller numbers of the material that has not decayed yet. So here things seem to make sense. However, if we go back to our solution of the first and the third problem, here we will see that in the limit when the time or the independent variable of our solution tends to positive infinity, then again we can compute the limit of that solution when time grows without bound, and under the assumption that k is a, let's say, constant real number that is strictly greater than 0, this limit over here comes out to positive infinity. And what does that mean? Does that mean that all hope is lost for our model of, let's say, population growth and information propagation? Well, the answer is not really, because we think that this model may portray or describe or predict a real-life situation reasonably well within relatively short initial amounts of time. For example, let's see, let me grab some red chalk. Sometime over here, maybe somehow up to this point over here, what we observe in reality and what our model predicts mathematically may coincide within a reasonable degree. However, in terms of physical matter that is present, for example, on our planet, everything comes in finite quantities. There is only a finite number of molecules of air on our planet. There is only a finite number of molecules of water on our planet. There's only a finite amount of sustenance, and so on. And that means that once, for example, our colony of primitive organisms reaches certain critical mass, for example, we'll portray that mass over here. Let's call it X with a fancy font over here, C for critical. That means that the biological sphere or biosphere or the life environment in which these creatures live will no longer be able to sustain that colony. And that colony, likely we think, probably will not be able to exist the way it existed during this initial time over here. Coming back to our problem of effectiveness of advertisement, where, let's say, we measure the independent variable t in time, of course, we can claim that the coefficient of proportionality can be made very, very small, and that is true. But just to show you how, what are we up against in case of the exponential growth. Let's say we'll come up with an estimate for the number e to the power of 365. This is basically, let's say, one non-leap year. And again, if you will say, Roman, look, you're not being fair over here, because with the playing with the value of the coefficient k, we can make this exponent smaller. And I agree with you, yes, we can. However, in a finite number of years, we will quickly again ramp up the whole thing to 1 year, and we will come back eventually to this number. So go ahead, play with numbers. You will see that this will be the case. Let us run a rough estimate of what this number looks like. In a fairly useless decimal expansion, the number e goes 2.71, blah, blah, blah. So here, definitely this number will be larger than 2 to the power 365. So far, so good. Now, if you're writing C code for many years, like I do, you know that 2 to the 10th power, this information is already burnt into your upper crust of your brain. This will be 1024, so this is still larger than 10 to the third power. So far, so good. So then 10 goes into 365. Let's be generous, 36 times. So this number will be larger than 2 to the 10th power, and 10 is raised to the 36th power. This is still larger, I'll continue over here, larger than 10 to the third. And then this guy raised to the 36th power. This now we switch to equality. 10 to the 19, 108. And then we decompose 108 like so. 10 to the 10th power times 10 to which power? 98 by the looks of it, 0, 0. So let's say this number right here represents the population of one planet Earth. So essentially what we're saying, if we play enough, if we torture this product over here long enough, eventually we'll come down to the number of people who know about the product P after some finite number of years, that will be expressed what? As the number of Earths of number of planets Earth population wise. That is, has 10 followed by what? 97 more zeros. This is incredibly large number. Is beyond any reason. Obviously, it is not realistic. Maybe a company C would like to have it so that many people are aware about their product P. But obviously, again, this is not realistic. This is precisely the situation which gives the reason for us in all these initial titles of the segments that you see in this episode to say unlimited resources. Now in the next segment, we will address the issue of how can we make this whole situation be more realistic. In other words, how can we come up with a mathematical model that takes the limitation of resources into account. And by that, what I mean is the following. Let's say we conduct the experiment over here where we enter a competition between our mathematical prediction and the real life situation. Again, we argue that initially, during the initial time over here somewhere, if we start dropping the points on the number of, let's say, people who know about product P or the number of living primitive organisms, these points will somehow hug our or sit on this curve kind of close. We will say, okay, we'll pacify ourselves saying, yeah, it's kind of reasonable. Probably that's what it is. But then after this population reaches the critical mass, or after the number of people who are interested in and know about the product P will kind of stabilize at this point, and possibly we again theorize, maybe this point will start jumping this way, and then eventually they will kind of stabilize, or maybe they will percolate, oscillate, we do not know. But this is one way to theorize. So fundamentally, what we will do in the next segment is we will find a mathematical way to grab our proverbial integral curve and bend it in such a way that it will, for example, initially behave kind of sort of the same, but then eventually this integral curve should really stabilize and approach a ceiling through which it cannot break through. Again, this is our theoretical machination, if you will, and we want to see how we can realize it with tangible mathematics. Now we can finally address the elephant in the room and construct a mathematical model of a real life phenomenon or of a phenomenon of information propagation through people over time, which takes into consideration the fact that the amount of resources available to us is not unlimited, but is limited. How do we do that? Well, cutting to the chase, we go back to our workhorse representation of the processes that we studied so far in this episode. And as I promised at the beginning of this episode, we keep playing with the structure of this all-important summon that reflects the small incremental change in a population of this or that items, or in the number of people who know about a product P during the realization that happened during the time delta t. So now, so far, we have been saying as our working assumption that that small increment in the number of people who learned about the product P during the time delta t is proportional to that time delta t raised to the first degree linearly, and it's also linearly proportional to the size of the audience who already knows about the product P. But we saw in the previous segments that this model leads to the unbounded solutions, and that model uh, considers that the resources at hand are unlimited. So how can we limit the resources at hand in a mathematical way? Well, if we think about it, and this is precisely the idea that you were supposed to or you were expected to generate if you manage to solve this problem correctly and on your own. And that idea at first blush seems to be a little bit counterintuitive, but if you think about it, then in a way it makes actually perfect sense. So now, in addition to the size of the audience that knows about the product P advertised by company C once, we say that that small increment in the number of people who learned about the product P during this time delta t is also proportional to the number of people who do not yet know about the product P. So in other words, one more time, let me repeat this to make sure that we're all on the same page, and in order to tell you guys that this is not a mistake. Our working hypothesis now, our assumption that will create a new mathematical model as we know it, is the following. The small increment in the number of people who know about the product P is not only linearly proportional to the size of the audience that does know about the product, but it is also linearly proportional to the size of the audience that does not know about this product yet. So how do we, again, going back to the mechanics of the equation problem solving approach, how do we convert the spoken language into the language of mathematics? Well, mathematically, we capture the number of people who do not know about the product P yet as the following expression. I'll write it in, let me write it in blue. It will be the size of our audience NA. This is the number that we are given ahead of time. And that number, in a sense, does represent exactly the limit on the amount of resources that we can work with. In our problem, where we study the effectiveness of advertisement, that number represents the size of the target audience. And in the problem where we studied the time evolution of population growth, what would that be? That would be the critical mass, exactly, yes. So here, the number of people who do not know yet about the product P at the time T and after the small time amount of time elapses is the target audience minus exactly x of t. This is our way to translate the spoken language into the language of mathematics. Now, if we go back to our previous models or the way we constructed our models, so technically, again, indefinite integrals, this and that, yada yada, branches of real axis of x-axis. But here, let's say, concentrate on the positive branch of the real axis or positive branch of the x-axis, or let's say we'll call it t, because in our study we always go by the point t. So how do we represent our solutions when the resources were unlimited. Well, we put, actually, yes, let me take it back. I apologize. This will be precisely x. This is not t. This is x. Let's make sure this is x. We took some initial point, x0. In the first problem, that was the number of live primitive organisms of this specific chosen type. In this problem, this will be the number of people who knew about the product P initially. Then we put the point x over here, and then we let this point roam the remaining x's over here indefinitely. For how long? For as long as it wanted to. But with this limitation over here, what we're essentially saying is that we're putting our variable x in a box. What is the size of this box? The size of this box will be, this will be NA. This will be the point x over here. And how can we interpret this? How can we interpret this, the structure of this summand shown over here? Well, if we construct a perpendicular through that point, perpendicular through this line segment, then stick the needle of the compass in the point x and draw a circle. Then this circle will intersect the perpendicular at 2 points. We pick one. Let's say we pick this point. And then this line segment is what? This is NA minus x. And this is exactly NA minus x. And now we have our box. This guy right here. X, NA over x. We give it the delta t thickness. You see the brick. We have our brick. This is the box x times NA minus x, x times NA minus x. Delta t, this guy, let's say this width, if you will be delta t. This coefficient you can explain all day long. Let's say we carve it up into 3 copies of cube roots of k, scale the sides proportionately, and there we go. But the important thing to understand here is the following. As the point x runs along this segment over here, let me put this thing. The size of this side that forms this box will adjust accordingly. So that means that when the point x reaches the point NA, then our box degenerates into a line segment, and in some sense this is the situation when our model stops working. That is how we capture the limitation of available resources in our mathematical model. And now again, what follows next is very familiar to us all. Let me go through these motions quickly so that we're all on the same page. We construct the difference between x at time t plus delta t minus x of t. Simply move this guy from the right-hand side to the left-hand side of the approximate sign. We still have k times x of t times NA minus x of t times delta t on the right hand side. Divide both sides by delta t, so we have x of t plus delta t minus x of t divided by delta t, approximately k x times NA minus x. Now we take the limit of both sides. Let's do it here. Limit as delta t tends to 0. We all know what's going on over here. Understand that we are manufacturing the first derivative of the function x of t. And here we, through the magic of taking the limit of both sides, we replace the approximation sign with the equal sign. Limit as delta t tends to 0 becomes k x of t times NA minus x of t. This is it. And here on the left-hand side of our equation now we have the first derivative. So it's x prime of t. In the Lagrange notation becomes k x times na minus x. And this is the equation that you were expected or that you should have produced if you solved this problem correctly on your own. And at the end of this episode, I'll show you how to do straightforward transformations and take it essentially into equation that looks like y prime equals to y and then some constant minus y like this. So this is essentially, structurally, they're exactly the same, but again, for the record and pedantically, this is known as the logistic equation, and that equation is named after the Belgian mathematician. His name is written over here. If I were to venture to pronounce it, Pierre Verhulst. He lived during this time frame over here, and now, since we obtained this solution, this equation, now we want to see how the solution of this equation can be obtained, and we will do this in the next segment. The next couple of segments will be optional. If you know how to solve this differential equation correctly on your own, you feel free to skip these segments and go all the way to the end of this episode and compare your solution and your answer to our answer. And here, for the benefit of those who have trouble solving this equation correctly on their own, I'll show how to solve this equation step by step. And as a side note, as a historical note, back in my time when I was in college, all our examinations in theoretical physics, mathematics, and computational sciences were held in a verbal format, which means that in real time we had face-to-face interrogation with the theoretical physics, mathematics, or computational sciences professor, where the professor could ask us anything within reason that pertain to that problem at hand. So that means that all the details that I'm about to generate, you are expected to generate in real time after given, let's say, 10, 15, 20 minutes to prepare. As such, we already know the program. We'll move from Lagrange to Leibniz, multiply, delta t, yada, yada. And fundamentally, what we will do is we will separate the variables because luckily, this is a ordinary differential equation of order 1 with separable variables. In other words, we spell out the definition, or we spell out another way to write down the fact that the formation here is the first derivative of the function x with respect to t, and thus we move from the Lagrange notation to the Leibniz notation, like so: dt equals kx na minus x. Again, I dropped the designation of exactly what the function x depends on. We know from previous segments that's the variable t. We multiply both sides of this equation by one copy of the first differential dt, and then we witness the fact that dt, these guys cancel out. We have dx equal to kx na minus x dt. Are the variables separated in this equation? No, not yet. To the differential dt, we have another function in x attached here. So our objective is to separate or sort all the variables in this equation in two different piles. One variables, all the material in one variable lives on one side of the equal sign, and all the other material that deals with the other variable lives on the other side. So here, what do? Well, we grab this guy, and we move him to the left-hand side. So now the equation becomes dx over x times na minus x equals k dt. That maneuver is understood. We divided both sides of this equation by this here expression, and at the end of this segment, or at the end of once we obtain the solution, I will analyze the so-called stationary solutions when x is 0 and x is equals to na. We'll see how that can be done. For now, we just blindly proceed forward. We charge ahead. And what do we do here? Well, we integrate both sides of this equation in the indefinite integral sense. And what do we have? We have the integral of dx of x over Na minus x, that is equal to integral k dt. We all know what that means. Integral dt, that is k times t plus the constant of integration, that will be t. We already know that much. Over here, things look a little bit slightly more complicated, but nothing out of ordinary. What do we do here? Well, the standard approach here is to decompose the rational function, this is called the rational function in x, into its partial fractions representation. In general, this can be done using the so-called method of indeterminate coefficients. We will not do this. This type of formation happens all the time. If you've been doing this long enough, you already know how to do it in your sleep. So here we just constructed on the fly. Over here, I'll do that. So how do we represent this guy? I'll write it down over here. 1 over x Na minus x goes into partial fractions as follows. 1 over Na times 1 over x plus 1 over Na times 1 over Na minus x. Again, do not just blindly trust Roman. Roman is just a human. Keep me honest, verify that this is the case. But once you do all the middle school arithmetics, you will see that this is the case. So now we use another property of indefinite integrals. The integral of this whole beautiful mess can be broken down, and the integral sign can be stuck or glued to each summand over here. So what do I have in the first case? In the first case, for the integral of 1 over Na times 1 over x dx, what do we have? 1 over Na times log of absolute value of x plus the constant of integration 1. Again, identically, whenever you do this, you are expected to produce the intervals where the solution that you produced is valid. Here it will be two intervals, from negative infinity to 0, from 0 to positive infinity. And what do we do once we move the integral sign through this sum over here? We apply it to this guy. So what do we have? The integral of 1 over Na times 1 over Na minus x dx. What do we do here? Well, the maneuver is standard. We move this usual suspect under the differential, and to balance this minus sign, we put the minus sign over here. If you want me to spell it out, then here it is. Minus integral over, let's say, Na d Na minus x over Na minus x. Is that understood? This is a straightforward maneuver, nothing extraordinary over here, but essentially we have this guy over here again. This material is the same. So what do we have here? We have over here negative 1 over Na times log of absolute value of Na minus x plus the constant of integration 2. But now when we put these two guys together, if we put these two guys together, what will we have? The multiplicative constant is one and the same in both cases. Would you agree? Modulo the sign over here, of course, but it's one and the same. So now we combine it, and we have 1 over Na times the logarithm, natural logarithm of what? Technically, again, absolute value of x over Na minus x, absolute value, plus constant of integration 1 plus constant of integration 2. So here, let's just be official and say that C1 plus C2 becomes C3. A sum of two constants is another constant. So here we will write plus constant C3, and we know that this beautiful mess is equal to, where do we have the expression for here? This guy, so this becomes kt plus the constant of integration t. Again, we see what's going on. We move this guy over here, minus c3, and we call this another constant, c4, for example. Let's call it c4, and this is our answer so far. And let me take a short break and erase all of this, and we will take, in the next segment, we will continue from here, and you already know what the program is. We need to simply isolate x and write it down in terms of the independent variable t. As promised, we continue from the expression that we obtained in the previous segment, and the overall goal of this manipulation is to isolate x and express it in terms of the independent variable t. What is the next maneuver? We have the size of the target audience NA over here hanging out as a body of our natural logarithm. What do we do with this guy? Exactly, we multiply this equation through by one copy of NA, and what do we have? We have the natural logarithm of the absolute value of x over NA minus x. That is equal to, let us carefully write down what we have on the right hand side, k times the size of the target audience A times our independent variable t plus, oh my, c4 times NA. But c4 is a constant real number. Let's say this is another constant real number. The product of any two constant numbers is another constant number. So we will Christian this guy as k. So far, so good. All right, very nice. In order to save the real estate and save you some time, guys, also, I will erase it. And now we understand where did this come from. This is plus constant k. Now what do we do? Well, now let us say we need to pedantically analyze exactly. Remember, the indefinite integrals, they're only valid over certain intervals. Once we analyze these intervals, we also have to square the whole business of what we're dealing with against these specific numbers. But now let it be written, let it be said, we're only considering the values. I'll write it over here, 0, x less than NA. So far, so good. We agreed on this interval, on this subset of real numbers. So from now on, we understand that because of this whole argument of the natural logarithm can be written without the vertical bars, without the absolute sign. So now, once we raise everything, we use these two expressions as powers for the exponent e over here. I'll write it like this. We'll understand what's going on. What will we have? We will have that x over NA minus x is equal to e to the power k and a t plus k. That maneuver everyone should be comfortable with. E to the power of log something is something, and that something is x over NA minus x. And the reason why we have the right to remove the signs for the absolute value of the argument of logarithm, because now we agreed that we're dealing with this subset of real numbers. We're interested when x, in the situation when x varies like so. So I will not be repeating it, this condition, this constraint on every line, but that is why we do that. Here we use the property of the exponential function, and we write it like this: e to the power of k times e to the power of k and a t. So far, so good. E is a constant real number. K is a constant real number. A constant real number raised to a constant real number is yet another constant real number. And we will designate this guy one more time. Let's say this will be, we'll call it A, another constant real number. So we'll rewrite it as A times e to the power k and a t. So what do we have now? Let's write it on this side. X over NA minus X is what? Is A times E to the power K times NA times T. Right? This side and this side, through a series of magnificent manipulations, each of which is legal, we came to here. We equated these two sides. Now, what do we have? In a way, we also have an equation in X, which we are to solve. Those who feel comfortable with manipulating this whole idea, this whole mess all the time, be my guest, you can do that. But for simplification purposes, let us do this. Let us write this equation as follows. X over NA minus X equal to capital E. It doesn't matter. This is just some material that is known to us. We don't really care. Let me fix my mistake. Like so. So this guy temporarily, this becomes E just for the purposes of manipulations in order to make all the upcoming manipulations transparent. So what do we do now? Well, this is typical middle school business. Let me continue over here. So we have X over NA minus X equals E. What does that mean? From here it follows that X is equal to E times NA minus X, and that means that once we spell out this product, we will have E times NA minus E times X. This is clear, right? Now we carry the term with X from the right hand side to the left hand side. What do we have? X plus E times X equals to E times NA. So far so good. So E is the common term over here. We factor it out. 1 plus E equals E times NA. And from here, what is X? X is, let's write it like this, NA, because X is measured still what? In the number of people who know about the product P advertised by the company C once. So times what? E divided by 1 plus E. See, this is our result that we were looking for. And now instead of E, we simply unwind and put in our complete expression that contains the independent variable T. Let me write it down over here. Then we'll take a short break. I will erase all of this and let's write this answer down here. X of T is equal to NA times, what is E? A times E to the power K NA T over 1 plus E to the power, A times E to the power K NA T. Is that understood? What we did over here? This is all should be transparent. Everyone should be able to follow. And okay, I made a royal mess over here. I apologize. Let me erase it and make it perfectly clear that what's going on in the numerator is the following. 1 plus A, the unknown constant that which we're about to recover, times E to the power K and A T. This is our temporary intermediate result, which is the solution of this here logistic differential equation, or an equation that carries the name of the Belgian mathematician Pierre Verhulst. So let me take another short break over here. I'll erase all these intermediate manipulations, but what will we do in the next segment? In the next segment, we'll recover the value of the constant A. And how will we do that? Well, we'll use the initial condition again. We will use the fact that the value of x at t that is equal to t0 will be x0 simply. And that will represent the number of people who know about the product P already. So in a sense, our expression, our equation that we will be working with in the next segment will look as follows. X0 is equal to NA times a to the power ae to the power k and a t over 1 plus a to the power e k and a t0, of course. Yes, I apologize. Okay, t0. So in the next segment, we will take on this equation, and the whole idea here is again to manipulate this material into submission so that we isolate A from this material over here. If you know what's going on and you see how to handle the rest, then feel free to fast forward to the end of this segment. Wonderful. I will leave it as an exercise to the members of our community to investigate what will happen if they will dance the dance with the initial value of time t0. But for the demonstration purposes, I will set that initial time to 0. And if we do that, so under the assumption that t0 is equal to 0, let's say we begin measuring the time in our experiment when the clock strikes 0, or we set it to 0, what will happen over here? Well, this exponents will collapse into the positive unity, and we will have the following expression: x0 is equal to na times a over 1 plus a. So far, so good. See? This is our initial condition. We obtained this expression under the assumption that t0 can be anything, and it can be anything, but that anything can be just as well 0. And for your own experimentation purposes, see what will happen if you drag this exponent around all the way. Here, for demonstration purposes, we will deal with this expression. So what will we have? We will have x0 is equal to na times a over 1 plus a. So now we have what? Again, we have an equation in a, and our goal is to isolate a and solve this equation for a. What do? We multiply this equation through uniformly by 1 plus a. And what do we have? We have x0 times 1 plus a is equal to a times na, the size of the audience, or the size of our target audience. Spell out this product: x0 plus x0 times a equal to a times na. Isolate the variable a on one side of the equal sign. x0 is equal to a na minus x0 times a. And then since a is one and the same, we will say that x0 is equal to a na minus x0. And what is a? Finally, a is equal to x0 over na minus x0. And in a way, again, it makes sense because the initial number of people who knew about the product P should not really be greater than the size of target audience, and this is our limitation of available resources. What do we do now? Now we take this value of A and insert it into which one? This expression right here. I'm sorry, let's take this, and we insert it over here. I will continue on your right hand side over there. I will erase this. You understand what happened here. So let me take the real estate over there on the right. So once we insert the value of A into the formula shown over here, we will have x of t will be na. What is this guy? x0 over na minus x times e to the power k na t divided by what? 1 plus x0 over na minus x0 times e to the power k na T. Again, all these manipulations honor this constraint. They all carried out under this constraint. And maybe again, this looks a little messy. Let's make sure that this looks good. This is a ratio times NA. Let's put it in the end over here. What kind of manipulation is coming up next? Well, we see that we can multiply the numerator and the denominator of this ratio through or uniformly by what? Exactly NA minus X. So once we do that, what will happen here? The difference NA minus X in the numerator will disappear. So we will write it as follows. X of T equals to, let me carefully keep this guy in the front, and then we will work over here. What will be left in the numerator? It will be x0 times e to the power k NAT. So far so good. This difference will cancel out with this term, but it will pop in over here. So here on this side in the denominator we'll have NA minus x0 plus x0 e to the power k NAT. So far so good. Now in theory we can already leave the things the way they are, but we can clean up this expression a little bit. So for example, we can divide the numerator and the denominator of this answer precisely by one copy of x0, because we have x0, 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 and it will jump over here. Let's do that. X of t will be NA times e to the power k NAT over NA divided by x0 minus 1 plus e to the power k NAT. Does that make sense? Yes, it does. It looks quite neat right now. And before we claim victory on this thing, what do you think while I'm erasing this material over here, because you guys keep good records of what is going on? Think about what would you do with this expression if you were putting this episode together. If you were Roman, what would you do? What is the next new word that's coming up? Exactly. What we do is we play some nice games with the exponent. Notice that the exponent here is present in both the numerator and the denominator. So we can get rid of this because it's not really clear what is going on over here. At a glance, it's difficult to predict how will our function behave as a function of time. So what we do here is the following. We multiply both the numerator by the negative k NAT, and we do the same thing to the denominator. So far so good. This is the positive unity. Something divide by something. As long as it's not 0, then we can do that. So we're essentially multiplying this whole mess by 1. It doesn't change the value. But once we move in these exponents with the negative powers, what will happen? When this negative power collides with this one, it becomes 0, so this exponent disappears. When this power collides, negative power collides with this positive power, it also disappears, so this becomes 1, and we only have to worry about this product, this thing over here. So let's write down the answer that will be our official result. It will be NA times 1 over, here we will have 1 plus gamma minus 1 times e to the power negative k NAT. And this is our result. This is an official solution of the logistic equation, or an official solution of the so-called Verhulst equation, differential equation shown over here. So what is gamma? Okay, that one is easy to explain. We simply took this ratio over here, the size of the target audience divided by the number of people who knew about the product P initially, who learned about it, let's say, through the advertisement campaign, and then the information started spreading through people by the word of mouth. And we named that ratio simply, we took this guy and we named them gamma. You can name it, I guess, anything you want. So what is the meaning? Let me write it down officially here. Gamma is NA, the size of the target audience, divided by X0, where the X0 represents the number of people who knew about the product P at the time T equal to 0. What is the meaning of this ratio? Well, it is easy to explain. The meaning of this ratio is the following. It tells us it correlates to the size of the group within which, for example, out of which one person definitely knew about the product P. For example, let's say gamma is equal to 2. That means that the ratio of the size of the target audience to the number of people who knew about it is 2. That, what does it mean? It means that in every group of 2 people, one person knew precisely already about the product P. Another way to say it is that every second person knew about the product P initially. If this value of gamma is equal to, let's say, 3, then what does it mean? 3 is the size of the group of people out of which one person definitely knew about the product P. Or another way to say it, it means that every third person knew about the product P, and so on. So with this number we can play. And in the next segment, as an extra for experts, I will analyze the so-called stationary solutions of this differential equation when x takes the values of the usual suspects. X equals 0, then x prime, or the velocity, if you will, equals 0, or when x equals to NA, the size of the target audience. If you're not interested, you can skip forward and continue watching this episode after that. This short segment is optional. It's an extra for experts, and in order to keep the size of this episode manageable, I already wrote some things down on the board for you. Put this video on pause at your leisure, examine this, keep me honest, but the idea here is the following. In theory, again, this is not the objective of this episode, but if we were in the land of the theory of differential equations, then we have to analyze the solution that we obtained to death, consider all sorts of cases, not only the case when x runs between 0 and the size of the target audience, when it's above, when it's below, what happens on the left of some asymptotes, what happens on the right. We're not going to do that again, but as a short demonstration of what this analysis might look like, we want to see what will happen in the situations when x is 0 or x is equal to NA, because these are special points when the velocity or the first derivative turns into 0, which means that the solution itself, x, remains constant. So one way in which mathematicians analyze this sort of things is that they consider the so-called epsilon neighborhood of a particular point, and the epsilon usually is taken to be strictly positive real number, usually quite small or as small as we like it. And sometimes we take the limit of whatever material has epsilon in it when epsilon tends to 0. So here we designate first derivative, putting on a head that reads a physicist. So from physics perspective, the velocity or the rate of change of the number of people who are aware of a product P, we can designate with v as velocity, and then it becomes just a function of x. So purely as a function of x, what happens when x is 0 and x is equal to NA? Well, in the first case, in the epsilon neighborhood of 0, this is the string of manipulations that we have. Here we have the term that is quadratic in epsilon. You can see over here epsilon squared, so we throw it out. And what do we have for the velocity of change of the number of people? Well, we have a linear dependency, and this number over here becomes what? it's an angular coefficient, which means that technically this stationary solution is not stable, or some people will say it's repellent. So these solutions tend to run away from it. And what does this situation represent? This situation represents the growth of the number of people who are aware about a certain product when these numbers are small, around in the epsilon neighborhood of 0. So the number of people who are aware and learn about the product, the velocity over here in this case grows, and the number of people who know product increases. On the other hand, if we look at the point NA, the target audience, again, in the epsilon neighborhood of the point NA, what will happen? Well, again, we take X, we represent it as NA plus delta, and then we simply insert N plus delta here and here. I did it over here for you guys. You can check my arithmetic. These two guys cancel out. Again, we multiply epsilon through, and here we get, in the case of the size of the target audience, we get negative angular coefficient of a straight line if we treat this here as a linear function. Again, negative k times epsilon squared is higher order derivative, high order magnitude, which that is very small. We throw it out and we only consider this. So again, this should really say approximately, and this one says approximately. And what does that mean? Well, the slope is negative, that it means in this case. And what does this case represent? Well, this represents a stable stationary solution, and some people say it is attractive because all guys tend to flow this way. And this situation represents the case when the rate at which the number of people learn about this product slows down. So you can take this analysis further on your own, you can play with it, but essentially, coming back to what the solution that we obtained, again, graphically these days, it's very straightforward to graph these things. Pick up your favorite graphing software. I use, for example, free software called GeoGebra. There are all sorts of other free graphical calculators. If you plot the solution, if you plot the graph of our solution in such a graphical calculator, you will see a nice smooth curve that actually approaches our 0 point from the left in quite reasonable fashion, then touches, crosses over at the point x0, which represents in our case the initial number of people who knew about the product P, climbs, and again here, see, the tangent will form an angle that is corresponds to positive derivative, this guy right here, this guy. So the number of people here grows, but once it flips over and tends to infinity, then the graph, as we wanted originally, bends, and then the the horizontal x equals an a becomes one of its horizontal asymptotes. It never really breaks through, it stays here, so the solution is stable. Here the rate at which the information is distributed from person to person or propagated from person to person slows down. And again, the very interesting and a very popular question in the entire theory of differential equations: what happens to our solution when the independent variable of that solution grows without bound? In this case, we're interested in the value of the limit of our solution when the variable t grows without bound, tends to positive infinity. In this case, that limit is straightforward to compute. That limit not only exists, but basically, essentially, in that many words, this guy, this factor over here tends to 0. This is whole thing annihilated. We have 1 na over 1 is na. And here is an amazing thing and an important conclusion that we draw, that asymptotically, our solution approaches a stable state where the number of people who know about the product P approaches the size of the target audience, regardless, and that is very important and very interesting observation, regardless of the initial conditions. Look at this. The limit of our solution It has x0 baked into it right here by the means of this gamma, but this is just syntactic sugar, it's there. So even though x0 is there, the limit of this solution when the time grows without bound, does it have x0? No, it doesn't. So this is an important also mathematical characteristic of our model, that our system tends to a state of stable situation where the number of people who are aware about the product, certain product, stabilizes around the target audience asymptotically. And that stable state will be reached regardless of the number of people who knew about the product initially. This is quite interesting. So for example, if you have your own, say, YouTube channel and you want to advertise it once, now you are armed with a mathematical tool. You have mathematical weaponry to investigate what will happen to the knowledge about, let's say, your channel over time. Measure time t in days, play with these numbers, play with this coefficient, make it, I don't know, 2 times 10 to the minus to the negative 6 power or some such. Estimate the size of your audience, play with these numbers, plot the graph and see what is going on. But again, essentially, one more time before we call it a day with this problem, I wrote this for you guys at the bottom right of your screen. The very important message that we take away from all this business is that our new model is still continuous, it is still one-dimensional, but it is a model in which we address limited resources, and our model produces bounded solutions because the horizontal x equals na is an asymptote, a horizontal asymptote of our solution. So the solution is bounded. We managed to actually quite nicely bend our integral curve, if you remember from the previous segments, and obtain a solution that behaves reasonably, just pretty much the way we want it. But still, because this is a new mathematical model, still, what does such a mathematical model produces on the output? An exact solution of an approximate problem. So approximations come from the assumptions, which we usually make in such a way that we can bend the upcoming mathematics our way, so that we can handle that mathematics. And that is the source of approximation. But after all the approximations have been booked and officially logged as an assumption or an axiom for this model, boom, that's it. There is no more games, no more maybe, no more if, that, but, or whatever. The solution that such a model produces is exact. And in the previous segments, you saw exactly how we produced this solution step by step. We didn't cut any corners. Valid mathematics throughout. One more time, please allow me to repeat myself. An exact solution of an approximate problem. This is it for the problem S2M21, and we will move on to the challenge next. Before we look at our next challenge, I just realized that I gave you guys my promise to tell you or to explain to you what should you expect in the textbooks, and I did not deliver on that promise at the end of the last segment. So here are just a few seconds. If we take the equation that we worked with in this episode all along, the logistic equation or the equation of Verhulst, then basically we carry this constant through into the parentheses over here like so, k times na minus k times x. Again, the product of two constants is a constant. Call it a, or whatever other symbol you like. And now, since we have kx over there in the parentheses, we can multiply this equation through by k as shown over here. Make a substitution, kx equals y, where y is a new variable. And now you will obtain this equation right here. And this is what most likely you will see in most textbooks. First derivative of y equals y times a minus y. A is a constant, and that is the equation that you will analyze to death with all sorts of conditions. And this is what most likely in many textbooks you will see as logistic equation. So now we're done with this guy. Now on to the next challenge, the mathematical problem S2M22. And it will be reasonably difficult, but it's doable. It's not something that is beyond your reach. You can do it. And the objective in this problem is the following. Knowing only the value of the so-called Euler-Poisson integral shown over here on the over the positive branch of the x-axis from 0 to positive infinity. This is the number a. Again, a is strictly positive greater than 0. For all a like that, it holds. The objective is to evaluate the Fresnel integrals shown here over, again, the positive branch of the x-axis from 0 to positive infinity for the trigonometric function of sine, and from 0 to positive infinity for the trigonometric function of cosine, using, again, that's the whole idea, using the problem solving approach that we're studying, using the equation problem solving approach. That is the thing. And as a hint for this problem, barring some really trivial manipulations, you ideally, if you solve this problem correctly using the equation problem solving approach, you will not be doing any integration per se. So that is a hint. And again, that episode will be our final episode in which we will be studying the equation problem solving approach. And the reason I want to bring this problem to your attention is just to show how versatile the equation problem solving approach is and how powerful it is. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will discuss my solution of the mathematical problem S2M22.